In this video, we present our approach to vision-only UAV state estimation for fast and aggressive flights without external localization systems. We develop a fully onboard estimation pipeline using only an IMU and a single monocular camera, capable of reliable operation during agile flight in GPS-denied environments. Visual Inertial Odometry, or VIO, is the standard method for onboard state estimation using only a camera and an IMU in GPS-denied environments. However, VIO suffers from significant drift and delays during aggressive maneuvers. Therefore, we also incorporate a landmark detector to correct VIO drift using detectable landmarks in the environment. At the start of the flight, VIO is initialized at the UAV's position and defines its own coordinate frame, which is connected to the world frame through a static transformation. As the UAV begins flying and performs fast aggressive maneuvers, VIO starts to drift, and its estimated states diverge from the ground truth states across all 6 degrees of freedom. Relying on VIO alone for state estimation often leads to crashes. Current state-of-the-art methods either rely on inaccurate VIO estimates, such as linear and angular velocities or the UAV's attitude, or require more complex hardware, including stereo cameras and rangefinders. In contrast, our approach compensates for VIO drift across all UAV states while using only an RGB camera and an IMU. Here is our estimation pipeline. VIO uses IMU and camera data to provide drifting UAV states, which are fused with camera measurements from the landmark detector to estimate VIO drift. Then we correct the VIO odometry using the estimated drift and fuse it with IMU data to reduce delay and capture aggressive UAV motion. Finally, the estimated states are used by the controller to track the pre-planned trajectory. In our paper, we propose a novel model of VIO drift, which is incorporated into a Kalman filter to estimate the drift. We then fuse data from VIO, the estimated VIO drift, and the IMU to produce the final UAV state estimate, as you can see in the equations. Our approach was successfully deployed at the A2RL Drone Racing Challenge 2025 in Abu Dhabi, where we advanced through the quarterfinals and semifinals to reach the final round among the top 4 teams out of a total of 210. The goal of each round was to complete 2 laps through a predefined sequence of 11 gates, and we completed multiple 2-lap runs at speeds of up to 45 kilometers per hour. Here you can see one of our flights. The 3-dimensional plot in the top left corner of this flight shows that the VIO estimate, shown in gray, is insufficient for agile flight in cluttered GPS-denied environments. In contrast, our approach provides accurate state estimates, shown by the blue to red trajectory, indicating speed from slowest in blue to fastest in red. We also performed real-world experiments on an outdoor track to compare our approach against ground truth values obtained from RTK. The outdoor track consisted of 6 gates, and the UAV was required to complete 2 laps. The 3-dimensional plot in the top left corner shows ground truth data from RTK, estimates from VIO, and values from our approach, where color indicates speed. Our approach tracks the ground truth smoothly, while VIO exhibits significant drift. We conducted numerous flights and performed a statistical evaluation comparing our method with state-of-the-art approaches and RTK values. Here is the table presenting the statistical evaluation of our approach compared to ground truth values and state-of-the-art methods across all UAV states, including position, orientation, linear velocity, and angular velocity. Compared to state-of-the-art methods, our approach reduces the root mean square error of linear velocity by 16%, orientation by 70%, and angular velocity by 88%. Our novel approach for vision-only UAV state estimation presents an accurate onboard pipeline for fast and aggressive flights using only a monocular camera and an IMU. Our approach achieves significant improvements in linear velocity, orientation, and angular velocity estimation accuracy in terms of root mean square error compared to current state-of-the-art methods. Additionally, it incorporates a novel drift model and directly fuses IMU data into the final UAV state estimate.